This is Hoheneufen Castle, about 10 kilometers away from where the camera is at. And this here is an ESP32, connected to a cheap OV2640 camera module. In the lab, this setup can transmit live pictures. I was wondering if this could also work over a distance of 10 kilometers and what kind of antenna I would need for that. Luckily, there are ways to calculate this. Let me introduce you to the freeze equation. This equation can be used to estimate the received signal strength, where lambda is the wavelength, Pt and Pr are signal powers at the transmitter and at the receiver, and Gt and Gr are their respective antenna gains. The antenna gain basically just tells us how much the antenna focuses in the main radiation direction. An ideal isotropic radiator would have a gain of 0 dBi. This typical omnidirectional antenna has a toroidal radiation pattern and a gain of 8 dBi. The r in the freeze equation is what we actually care about, the distance between the two antennas. At a first glance, this equation looks pretty bad for us, given that the r is in the denominator and gets squared. The good news is that even consumer-grade Wi-Fi equipment is really good at decoding signals with less than femtowatts of signal strength. So good actually that we commonly use the logarithmic decibel scale in order to describe tiny power levels. In order to convert some power level into decibel milliwatts, or dBm for short, you just have to take 10 times the decadic logarithm of the signal strength in milliwatts. This way, 100 milliwatts become 20 dBm, 1 milliwatt becomes 0 dBm, and 1 microwatt becomes minus 30 dBm. If we apply the same idea to the freeze equation and take 10 times the logarithm of both sides, the difficult multiplication gets replaced by simple addition. Since all we care about is how much the power level changes if we increase the distance between transmitter and receiver, we can also write this as some constant value minus 20 dB times the log of r. So if we want to use the same setup to transmit over twice the distance, we have to double r. By logarithmic identities, we find that this only contributes to a constant summand of minus 20 dB times the log of 2, which is approximately minus 6 dB. To put it bluntly, every time we double the distance between the two antennas, we lose 6 dB of signal strength. So what can we do against that? We can't just increase the transmit power, since most countries' laws prohibit that. A common misconception is the idea that a better antenna at the transmitter will drastically increase our range. This is in fact not true if we abide by the law. Regulations in most countries state that the equivalent isotropically radiated power, or EIRP for short, must not exceed 20 dBm. So adding a better antenna to the ESP32 won't do any good, since that would force us to reduce the transmission power. Instead, we need to rely on a really good antenna on the receiving end. While I'm preparing the receiver setup, some friends of mine ascend the mountain towards Hoheneufen Castle. This historic location has the advantage of being an easy to target landmark with perfect line of sight and no surfaces nearby that could cause interference. After fixing some last minute firmware bugs in the castle courtyard, we were ready to transmit. On the receiving end, I'm mostly using cheap consumer grade hardware such as this USB Wi-Fi adapter. The only uncommon gadget is this 60 euro 24 dBi directional 2.4 GHz antenna. 24 dBi implies that we should be able to cover a distance of up to 16 times more than usual with this antenna. As it turns out, just manually pointing the aerial in the general direction of the castle is enough to get decent signal strength. The image quality might not be the best, but picking up signal from the ESP32 from a distance of 10 kilometers was no problem at all. At this point you might be wondering how it is possible to only receive data from the ESP32 without sending anything. Well, I do have one confession to make. I'm technically not abiding by the Wi-Fi standard in this case. Typical Wi-Fi specifies access points and stations that need bidirectional communication. In my mode of operation, however, I'm using the receiver in what is known as promiscuous or monitor mode, while I'm exploiting functions hidden in the ESP32's Wi-Fi stack in order to send arbitrary data. Nevertheless, it's just amazing how this little Wi-Fi chip can send data over such a long distance.